Alright, so this is going to be a video about L'Hopital's rule. That's kind of how you pronounce this, L'Hopital's. Some people kind of say like La Hospital. It doesn't really matter, but the correct way you're supposed to say is L'Hopital's. This is for sufficiently nice functions. It just basically means any of the functions you're really going to see in AP Calc or just regular Calc 1. Functions f of x and g of x. If the limit of f of x as x approaches a is equal to the limit of g of x as x approaches a is equal to 0, or both the limit of f of x as x approaches a is equal to positive or negative infinity, and then the same with the limit of g of x as x approaches a is equal to positive or negative infinity. If you take the derivative of the top divided by the derivative of the bottom and take the limit of that, if that exists, then the original limit that you might be looking for, like this one right here, this limit of f of x over g of x as x approaches a is equal to the actual derivative of basically the top and the bottom. This basically helps us take a way simpler limit because we just took the derivative of it, which usually makes the function a little bit easier to work with. And then this remains true if a is any constant or positive or negative infinity, which we're going to see in some of our examples below. So that's basically what L'Hopital's rule is. It might be hard to understand with all this lingo. So what I'm going to do is do these 4 examples here, and hopefully that makes more sense about what L'Hopital's rule is all about. Okay, so for this first one right here, it says the limit as x goes to infinity of this function divided by another function here. These would be considered sufficiently nice functions to use L'Hopital's rule with. Basically, you could actually solve this using the stuff that we covered in the limit unit, where since x is going to infinity, you can kind of ignore those constants because they're just meaningless in the grand scheme of things if we just directly plugged in infinity. So you would end up with something like 2x squared minus 3x, and get rid of that 7 because it's just meaningless because we're going to infinity, divided by x squared plus 4x, again getting rid of that plus 1 because we're going to infinity with this x, this 1, and this 7 are just completely meaningless for this argument basically. Now from here, what we can do is we can factor the top. So that's basically what we're going to do here is we're going to factor the top and get x times the quantity 2x minus 3. So basically I'm just going to cross these out here and then do the same thing on the bottom. So you're going to factor out an x times the quantity x plus 4. So that's all going on here. These x's are going to cancel, so that x and that x are going to cancel. And then if you try to do direct substitution again, x is going to infinity. That's 2 times infinity minus 3. This 3 is meaningless. Infinity plus 4, that 4 is meaningless. And now you end up with 2x over x here. So this x is going to cancel here, and you're left with 2 over 1. So our final limit, our final answer to this limit problem is equal to 2. Now, you can do that without L'Hopital's rule. Some other problems you really can't do without L'Hopital's rule, but I just kind of wanted to show you one where it does work if you don't use L'Hopital's rule. Now we're going to do this exact same problem, only we're going to use L'Hopital's rule, and hopefully you see that it's a little bit easier just to use L'Hopital's rule rather than trying to find the limit algebraically. So first thing we're going to do is try to do direct substitution. You end up with infinity over infinity. So you get infinity over infinity, which is one of the things in the rule that need to be true. So the limit of f of x as x approaches a equals positive or negative infinity, and the same thing with g of x. So if you plugged in infinity for both the top and the bottom, you get infinity and infinity. So that means if we take the derivative of the bottom and the derivative of the top, we should be able to find this limit. So let's try that out. So we're going to do the limit as x approaches infinity. And we're going to do the derivative at the top, which is just going to be 4x minus 3, just using power rule. The derivative of 7 is 0. We're going to do the same thing on the bottom. So you're going to have 2x plus 4. Okay. Now from here, if you do direct substitution, you plug this infinity, you get 4 times infinity minus 3, so you still get infinity on top, and you still get infinity on the bottom because it's 2 times infinity plus 4. But again, with L'Hopital's, if you have infinity over infinity, you should be able to just take the derivative of that, of the top and the bottom, and hopefully get an answer. So that's what we're going to do now. The derivative of the top is going to be 4, the derivative of the bottom is going to be 2. 4 over 2 is equal to 2. And if you remember, that's the exact same value we got if we did it algebraically. Here we both get 2. So that's basically just showing how L'Hopital's works. You just do the derivative of the top over the derivative of the bottom and simplify as much as you possibly can. Again, this only works if it's 0 over 0, infinity over infinity, or negative infinity over infinity. Let's do some more examples of this, but also before we go on, it's probably important to say that do not use quotient rule on this, even though you're actually doing quotient, even though these are rational functions. You do not want to do quotient rule on this. Just take the derivative of the top divided by the derivative of the bottom. Do not get it confused with quotient rule. Okay, this next one here. First thing I'm going to do is try to plug in pi here. We get pi squared minus pi squared, so we get 0 on the top. Okay, if you plug in pi here, sine of pi is equal to 0. So because we have a 0 over 0, we can use L'Hopital's rule. So I'm going to take the limit as x approaches pi, and I'm going to do the derivative of the top, which is 2x. The derivative of pi squared is going to be 0 because it's a constant. The derivative of sine x is cosine x, so I'm going to write cosine x here. Okay, now what we want to do is try doing direct substitution and see if we still get a 0 over 0. So if you do direct substitution here at the top, you end up with 2 pi over cosine pi. Now, cosine pi, you have to kind of know your unit circle here is equal to -1. So you're going to end up with 2 pi over -1, which is going to be equal to -2 pi. Okay, so that's basically how you do that second one. The answer should be -2 pi. All right, for this next one, it actually shouldn't say sine x minus 1. This is actually supposed to say secant x. I just kind of wrote it wrong when I was doing this problem. So it's supposed to be secant x minus 1. That's just a typo on my part. So if you put in 0 here, secant of 0 is going to be 1. So 1 minus 1 is 0. So you would end up with 0 on top. Sine of 0 is 0. So you have 0 over 0 here. This means that we can use L'Hopital's rule for this. So what I'm going to do is do the derivative of the top and then divide it by the derivative of the bottom. So the derivative of secant, if you actually worked out all the math, it would be equal to secant x tan x, and the derivative of that minus 1 is going to be 0, and we're going to divide this by the derivative of sine x, which is cosine x. So you end up with something like this. Okay, so now we can try to do direct substitution. So put in 0 for secant right here. Secant of 0 is going to be equal to 1. All right, tan 0 is going to be equal to 0. And then this is all divided by, if you plugged in cosine of 0, which is equal to 1. Okay, well 0 over 1 is just going to be 0. So you end up with a limit for this one being equal to 0. Again, notice the typo here. That should have said secant x, not sine x minus 1. All right, and last but not least, we have the limit of x times ln x as x approaches 0 from the right side. Okay, now this doesn't actually look like you can use L'Hopital's rule, but if you did try to plug this in, you would have 0 times basically ln of something approaching 0 here, which would end up being undefined. So you can't, it's technically still undefined, but you have one thing going to 0, the other one thing basically going to infinity. So you can't actually do anything with this, but to use L'Hopital's rule, we're basically going to rewrite this. So I'm just going to write this equal to, and rather than doing the derivative, because we need a numerator and a denominator here, I'm going to make this where ln x is on the top divided by, now since x is regular, I'm going to actually just make it x to the -1 on the bottom, because right here it's x to the 1, and if you put it to the bottom, then you can just make it x to the -1. So now we actually have a rational function that we can try to find we can find the derivative of the top and the derivative of the bottom. If you plugged in 0 here, you would have undefined, and then this is technically 0 to the -1, which is undefined as well. So undefined over undefined, or infinity over infinity, since x is approaching it, you'd be able to use L'Hopital's rule. So here we go. We're going to do the derivative of the top here. So the limit as x approaches 0 from the right, the derivative of the top is 1 over x. The derivative of the bottom is going to be -x to the -2. So now what you can do is you can try to plug in 0, but when you do that, if you try to plug it at the top, you have 1 over 0, which is undefined, and then this is going to be -0 to the -2, which is also undefined. So what I'm going to do is clean this up, basically. So I'm going to make it look like everything's just on one line, because some things might cancel. So we're going to make x to the -1 times -x squared. Okay, now I basically put this bottom one on top, so I had to change that sign from a negative to a positive. Now from here we can simplify this by adding the bases are the same, so we can just add the exponents. So it's going to be -x to the first. Okay, so we have the limit as x approaches 0 from the right of -x to the first. So you can just plug 0 right in here and you get -0, which is equal to 0. So it's not very exciting, but that's basically how you do them when you have something that's not a rational function, but you still want to be able to solve it. You have to basically just turn it into a rational function like I did right here. So that's L'Hopital's rule. If you have any questions about anything in this video, let me know.